Okay, so some more comments about solving modular equations. For simple equations like this, you can easily figure out that you just have to multiply by 2 both sides so that you get 6x congruent to 2, but 6 is congruent to 1 mod 5. So this immediately becomes x is congruent to 2 mod 5. Now, before I move on to some other examples, I want to point out that this means x is a number where if you divide by 5, you get a remainder of 2. That's what it means, right? You can rewrite this in the following way. See, if you subtract 2 from the x, when you say a and b are both congruent mod n, that means if you subtract them, then that difference is divisible by that n, right? So x minus 2 will be something that's divisible by 5. And another way to say it is that x minus 2 is a multiple of 5. Is that okay? And you can move the 2 to the other side and you get x equals to 5k plus 2. And in fact, you can just go from here to here straight away by saying that, oh, x is a number. If you divide by 5, you get some quotient, and 2 is the remainder. That's just another way of saying the same thing, right? Okay. So either way, whether you use the definition that if you have a equals to b, then subtract that should be a multiple of this number, or you just go straight here, the end result is that saying that x is congruent to 2, mod 5 should be thought as x is a number, which is 5 times some unknown number plus 2, okay? Now, since this k can be anything, this is not a single number that's a solution. That's actually saying x could be 2, and then add 5 to it 7, add 5 to 12, And you can also go by plugging in -1 as well. If you plug in -1, that's -3, and then you subtract 5, -8, -13, and so on and so on. Okay, so these are, all of these are possible solution to this. Okay. In fact, you can check right away. Let's say x is 7. What's 7 times 3? 21, right? And then if you mod by 5, if you divide by 5, what's the remainder? That's 1. So it does work, right? Okay. So that's what it means to solve a modular equation, but let me show you a different example. What if you have 2x is congruent to 1 mod 6? Now, this time, if you try to do anything, you'll see that it doesn't work. Right? There's no number that you can multiply both sides so that this thing, when multiplied, turns into 1. So you can say mod 6, what are the possible numbers? 1, 2, 3, 4, 5, right? You try all of them, none of them will give you a 1. And the reason that this time it doesn't work is because 2 and 6 are not co-primes. Okay? If they are co-primes, then there's a guaranteed via some things that we learned last time that you should always have something that you can multiply both sides. So this turns into 1. If they're not co-primes, then such a thing doesn't work. Okay? So now what? Well, to further investigate what's going on, we can still use this idea that we just had. Okay? So saying that 2x is congruent to 1 mod 6 means 2x is something that if you divide by 6, there's some quotient that we don't know about, and then 1 should be remaining. So this is the same thing as that. The above is same as that. Now let's move the 6k to the left side and see what it's saying. Do you see something strange about this? If you factor 2, here's what you get. Now, remember that when we're talking about modulo, we're assuming all the variables are integers, right? So you have some integers times 2 equals to 1. Why is this impossible? Why is this impossible?
Because you can't multiply something by 2 and get 1.
Yeah, what are the factors of 1? Just 1. Or you can say negative 1 times negative 1 is also 1, right? So things that divide 1 are only 1 or negative 1. But you're saying that 2 times some another integer is 1, so that means 2 is a factor of 1, which is clearly not true, right? You see that? Yeah. So this is impossible since 2 is not a factor of 1. Okay. So what that means is that this equation is an equation which does not have any solution. Okay. So you know, in linear equations, the things that you learned in middle school, you rarely get an equation that doesn't have an answer. But there are some cases, right? So for example, if you have like 2x equals to 2x plus 1, does this have an answer? It does not, because if you subtract 2x both sides, you end up with 0 equals to 1, which clearly doesn't work, right? So there are some rare cases, even in the usual equations that you know very well, that doesn't have a solution. Just that in modulo case, there are more than one possible ways that you might not have a solution, which is of this type, okay? All right. So what about this case? What if you have 2x congruent to 4 mod 6? Okay, let's think about whether this one can be done. Again, you can try any numbers from 1 through 5. There's no way to turn this, multiply a number to this 2 to get a 1. It simply doesn't work. And if you think about it, the reason is anything times 2 will be an even number, right? And if you divide by an even number, the remainder will have to be an even number as well. So that's why there's no way to get a 1, okay? And this is in general true. If you have a number here, and this one has a common divisor, then whatever you multiply to this one will always be divisible by that common divisor. So that way you won't have a way to make it into 1. Okay, but let's try to write it like this form. So if you write this in a usual equation form, what does that mean? 2x is what? 2x is equal to? See if you can rewrite it like this one. So congruence relation, you can get 2x equals to?
4 plus 6k.
Yeah, 6k plus 4. Or 4 plus 6k, either is good. Okay. All right. Now that seems to be okay. There's, in fact, if you look at this, you can divide both sides by 2, and you get x equals to 3k plus 2. But what that means is that, see, this one is not modulo 6. So what that means is x is congruent to 2 mod, not 6, but mod 3. Okay. If you want to convert this to mod 6, here's something you can do. You can actually think about the explicit numbers that give you 3k plus 2. So what are x is? X could be 2. What else? 5, 8, 11. You could also have -1, -4, something like that, right? Okay, so 2 is 2 mod 6. 5 is 5 mod 6, right? So 2 is congruent to 2 mod 6. 5 is congruent to 5 mod 6. What else? 8 is congruent to, if you do 8 mod 6, what do you get?
2.
Yeah, 2, right? If you divide 8 by 6, you have a remainder of 2, right? So 8 is congruent to 2. How about 11?
5.
5, right? So you can see that it's mod 6, this turns into 2, 5, 2, 5, 2, 5, right? This will be 5, this will be 2, and so on and so on, okay? Good? Yeah. So this actually means that if you go back to the same modulo system, you have x congruent to 2 or 5 mod 6. That's what it means. So this, and this is very different. See, in the regular equation world, when you write a linear equation, you always have just one solution, right? And only when you got to quadratic equations, you have two solutions for one equation. But here, this is just a simple looking linear equation in the modulo system. But when you solve it, you already get two solutions. Okay? And it gets even worse. You can write seemingly simple ones that have 3 solutions, 4 solutions, many more. Okay. Okay. So let me try to explain what's really happening here. I said that you are not allowed to divide in modular equations, right? And the reason for that was because division usually produces fractions which are not allowed. Okay? But here, 2x congruent to 4 mod 6. Here, if you divide both sides by 2, that's perfectly okay, right? If you divide by 2, that still works. So if you don't get a fraction, you are allowed to divide, okay? But there's a catch. If you divide by 2, you get 2x over 2 congruent to 4 divided by 2. None of them are fractions. This is just 2. That's fine. But if this number happens to be also divisible by that number that you're dividing both sides by, then the rule is that you have to divide that as well. So 6 also has to be divided by 2. Okay? So you get x congruent to 2 mod 3. Now, on the other hand, think about this case. 2x congruent to 4 mod 5. Okay? In this case, you can divide both sides by 2 and get that. And because this is not divisible by 5, you leave it as 5. And that's still fine. Okay. So, as you can see, we went from here to there by explicitly trying to think about what's going on, right? But it turns out that if every one of these are divisible by some number, and you rewrite in this form, then that number still divides all the terms so that you can divide them, and the resulting thing is the same as taking all of these numbers and dividing by that that number, dividing by 2 in this example. 2 divided by 2 is 1, 4 divided by 2 is 2, 6 divided by 2 is 3. That's what I'm writing over here, okay? So that's like a shortcut. To see why that works, you have to rewrite in this form and observe what's happening, right? Yeah. But over here, when 5 is not divisible by 2, you can still do this. You can divide, and this is the result you get, okay? Now, since I did this without really showing you why, I didn't like prove why, so let's try to get the same answer a different way. How do we solve this again? Multiply what both sides? What do I multiply both sides to solve this? 3, right? If you multiply by 3 both sides, then this is 3 times 2 is 6, 6 mod 5 is 1, so it's 1 times x. 3 times 4 is 12, right? But what is 12 congruent to mod 5? Just 2, right? So that's what you get. Exactly same as before, right? Right? So we verify that it's indeed possible to divide both sides by 2 if they're both divisible by 2. Right? Because this other method that always works even if you can't divide gave us the same answer. Right? To see what's really going on behind the scenes, see, modular arithmetic is something that we're just trying to understand. We just learned how to do it. Anytime you're suspicious, you should always go back to the regular equation and see what's going on. So, for example, if you want to really know what's going on, you should change this into 2x is equal to 5k plus 4, just like that. Okay? So there's some k where this is true. Now, it requires slightly more argument than before. So you first subtract the 4 this side, and then you get 2 times x minus 4 is equal to 5 times k. Now, does 5 have 2 as a divisor? And the answer is no. 5 is only divisible by 1 or 5, or negative 1, negative 5. So it's not divisible by 2. That forces k to be what? K to be divisible by 2. K should have a factor of 2. Okay? So you can say, since 2 does not divide 5, okay? This is the, so when you say 2 divides k, this symbol means divides, okay? Yeah. Since 2 does not divide 5, and it's a factor on the left side, right? 2 must be dividing k. And that means k is 2 times some other number, say t. Okay? If k is 2 times some other number, you can plug that back in and you get 2x equals to 5 times 2t plus 4. And now see that all of these are even, so you can divide both sides by 2. And if you divide both sides by 2, you get x equals to 5t plus 2. And what does this mean? It means that x is indeed congruent to 2 when you do mod 5. That's what this means, right? X is, if you divide x by 5, there's some quotient and 2 is a remainder. That's what this means. So you can make this kind of argument to see that it's indeed possible. Okay. So let's summarize what we have seen so far. Summary. If A is congruent to B mod n, then you can always multiply something both sides. It's always possible. Okay. So that's number one. Number two, if GCD of A and N are co-primes, if they don't share a divisor, then there exists some B. We'll have to find it still. You have to find it either by trial and error, or you have to use the Euler-Toshan function or whatever, okay? Yeah. So there exists some B so that A and B are inverses of each other in modulo n. Yeah, in other words, if 2 and 5 are co-primes just like that, they don't share any divisors, right? Then in that case, you can multiply something both sides so that this product turns into 1, which is the basis for being able to solve modular arithmetic. Okay, so in this case, if you multiply by 3 both sides, this turns into 1, right? So this justifies the case that the conclusion is, or the corollary is like something, if you know something, there's an implication, okay? So AX congruent to C mod n has a solution in mod n, okay, if GCD AN is 1. So if these two numbers don't share a common divisor, then you can always solve this. I should really say it has a unique solution in mod n. Okay. All right. Number 3. If D divides A and D divides B, A is congruent to B mod n, but D does not divide n, then A congruent B mod n, from this you can divide both sides by D. And you don't have to change this, okay? I made a mistake, sorry. It's stronger than that. GCD of N and D is 1. Then this is true, okay? 4, if A is congruent to B mod N, and all of these are divisible by D, then A over D is congruent to B over D mod N over D. That's what you have to do, okay? So, going back, let's see the following case. If we have 8x congruent to 6, no, not 6, sorry, 4 mod 6. Let's think about this example. All right. If we try to divide by 4, it doesn't work with 3, neither 3 or 4, because 4 and 6 does share a common divisor. Okay? So this doesn't apply. Okay? And since 4 doesn't divide 6 at all, this doesn't apply either. So you can't just divide by 4 right away for this one. You have to do it in 2 stages. You first have to divide both sides by 2. So solution, divide both sides by 2. And because 6 is divisible by 2, you have to divide that as well. Okay? And that gives you 4x congruent to 2 mod 3. Right? But 4 is 1 mod 3, right? So in our case, x is congruent to 2. And that's the answer. Okay? Now, if you want to convert this into mod 6, you have to think about what this means. X is like 2 or 2 plus 3 is 5, 5 plus 3 is 8. And mod 6, you have 2 or 5. Oh, we had this before, right? So again, this is 2 or 5 mod 6.